the deep dive. We take those sources you share and really dig into the core ideas just for you.
Yeah.
And today, we've got a really cool crossover, actually. How some, well, seemingly abstract math concepts,
It's like differentiation and integration.
exactly how they show up in something you can actually, hold. Like yogurt, specifically yogurt spoilage.
That's right. It's a great example if you're maybe looking at calculus and wondering, where does this stuff actually apply?
Huh?
And your source materials, they give us this fantastic specific case, modeling how farm-based yogurt spoils, especially thinking about temperature changes.
Okay, so that's our mission for this deep dive then. Let's unpack how these concepts like derivatives are used here, drawing right from your sources.
Yep.
And why this connection is, well, relevant, especially if you're maybe working through calculus right now.
Okay, let's dig in. So the sources really zero in on temperature, right, as a key factor in spoilage.
Makes sense.
And think about what spoilage actually is. It's a change happening over time.
Right, not instant. It develops.
Exactly. And that change, it isn't constant. It speeds up, it slows down, depending on the conditions, like temperature.
Yeah, okay. Like leaving yogurt out on the counter versus, keeping it super cold in the back of the fridge. Totally different speeds for going bad.
Precisely. And that speed, that rate, the yogurt's quality is declining. That's exactly what a derivative can help measure.
Ah, okay. So the derivative is about the rate of change.
Yes. The derivative of some measure of quality, maybe it's freshness, or pH like you mentioned before with respect to time, tells you how fast that quality is dropping at any specific moment.
Okay, so if your sources tracked, say, a specific quality score for the yogurt, the derivative of that score over time gives you the instantaneous spoilage rate, like how fast it's going bad right now.
You got it. Exactly. And here's where the sources get really interesting, linking it to temperature.
Right.
They highlight that this spoilage rate, it isn't just some flat number. It depends heavily on the temperature. Your sources talk about models, often used in microbiology, showing that the bacterial activity driving this spoilage, well, it often doesn't just increase steadily like in a straight line with temperature.
So what kind of relationship did the sources point to? Is it more like exponential?
Often, yeah, something like that. The sources hint at models maybe inspired by chemical kinetics,
Okay.
sometimes using equations that link microbial growth, and so the spoilage rate directly to temperature, maybe through parameters, kind of like you'd see in an Arrhenius equation.
Wow.
Which means the function describing that spoilage rate versus temperature, it's likely nonlinear, maybe even exponential, like you said.
So it's not just a bit hotter means a bit faster. It's potentially a bit hotter means way faster spoilage.
Pretty much. That's a really specific insight from the sources about how the math actually models the reality here.
And if you can quantify that rate, that allows for some serious prediction, doesn't it, for the producer?
Oh, absolutely crucial. If a farm knows how fast their yogurt spoils at, say, 5 degrees Celsius versus 10 versus 20, based on these derivative models,
Yeah.
they can predict shelf life way more accurately. They understand the real impact if the temperature goes up briefly during transport, for example.
Right.
One source even mentioned how knowing this rate could have potentially saved a whole batch lost when a fridge failed. They could have modeled just how fast it would spoil at that higher temperature.
That makes the connection super practical. It takes this, abstract derivative idea and applies it to preventing actual financial loss for a farm.
And that brings up the next level, right? If the derivative gives us the rate of spoilage at any moment, what about the total spoilage, the accumulated amount over, say, a whole day or a week, especially if the temperature isn't constant?
Ah, okay. So that's where integration comes in.
Exactly.
So if the temperature bounces around warmer during shipping, colder in the store, you'd integrate the spoilage rate.
Which itself is changing because the temperature is changing.
Right. You integrate that rate over the whole time period to find the total change in the yogurt's quality, like the total accumulated spoilage.
Precisely. Integrating the rate of change gives you the total change, the accumulated effect.
Yeah.
So yeah, you'd integrate that temperature-dependent derivative function over the whole journey.
From farm to fridge.
Farm to fridge, yeah. To predict its final quality or check it hasn't gone past some spoilage limit mentioned in your sources.
Okay, so let's pull this together. We've basically seen how your sources use derivatives to model the rate yogurt spoils, how that rate depends heavily, maybe exponentially, on temperature, and then how integration builds on that, letting you figure out the total spoilage over time, especially with real-world temperature changes.
It's a powerful illustration, really. Shows how these fundamental calculus tools, differentiation and integration, they're not just stuck in textbooks. They are vital for understanding and managing dynamic processes like food spoilage in very specific practical ways.
So for you listening, maybe as you're looking at derivatives and integrals right now, think about this idea. Rates of change and accumulation. Where else, beyond this farm yogurt example, where else in the world around you might these math tools be secretly at work? Quantifying how things change, how effects build up over time, definitely something to think about until our next deep dive.